So, welcome to the fourth lecture. Today we are going to speak about Taylor's theorem for functions of more than one variable. It is a very boring stuff actually to just say I will do Taylor's theorem and blah 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 blah. Those who have done calculus of one real variable has definitely heard of the name of Taylor's theorem, not Taylor who does your clothes, it is a English title, Taylor. And possibly people do not bother about who this Taylor was. His name was, though I think if I have not, I remember correctly, I have written his name in my one variable lecture also. His name was Brooks Taylor, and Brooks Taylor was a student of Newton in Cambridge, and Newton was interested in the binomial theorem, and he had actually used binomial theorem. He used to teach this to his students, he used to lecture this to his students, and from there on Brooks got an idea that for a general function how the binomial theorem, the expansion of the binomial theorem can be used to in such a way that the coefficients get related with the binomial coefficients. That was the idea of Brooks Taylor. You try to expand the function x, take the function x to the power n and just do the Taylor's theorem that you know from calculus of one variable. I do not remember at this moment what I did in calculus of one variables. It is very difficult to actually go back and really make a check, but it is not a bad idea that if I start telling you what a Taylor's theorem is. See, Taylor's theorem is used to approximate the value of a function which might be difficult to compute. For example, I say okay, compute sine of 31 degree. You say oh, it is not a problem, I know sine 30 degree. So, I can write this as, so you can write this as sine 30 cos 1 sin A cos B plus cos A sin B. So, putting sin 30 and cos 30 value is alright, not a problem. But what about sin 1 and cos 1? That is not so easy to find out. You tell me what is sin 1 degree. If I ask you, unless you have a trigonometric table in front of you, you cannot tell me what is sin 1 degree right away, right? I can't tell you, let me be very frank. How can I find sin cos 1 degree? How can I find cos 1 degree or say sin 1 degree? That was the question, computing functional values which are difficult to compute. So, what I do is that I can immediately get a good approximation by using the Taylor's theorem. Why? Because Taylor's theorem depends on only 4 fundamental arithmetic operations of addition, subtraction, multiplication and division. Only with these 4 operations you can take a known function value and estimate very fast an unknown function value. For example, I know sin 0 degree is 0. And I know that cos 0 degree is 1, and then I can compute the derivatives of sine at 0, sine first derivative, second derivative and all, and keep on giving a better and better and better estimate of the function. So, I can make, so those who know some, those who remember their calculus of one variable, sine 1 degree can be written as sine 0 degree plus 1 degree. So, 1 degree is the difference. So, it is sine of 0 degree, this is f of x plus h, which you already know, sine of 0 degree plus sine dash at 0 into 1 degree plus some error. So, roughly if you want to estimate sine 1 degree or maybe 0.001 degree if you want, is sine of 0 degree, which is 0. So, roughly, and what is cos of a very rough estimate is sine 0 is 0 plus sine of derivative of sine is cos. So, cos of 0 degree into 1, and we are not taking the error for the moment. So, sine of 1 degree has a rough estimate of cos 0, which is 1. And those who remember their trigonometry class or those who remember the Taylor's expansion and those who remember the physics class, you will see when x is very small, physicists often use the fact that sin x can be approximated by x. Here you see that is exactly what is happening. So, a very fast estimate, of course, you can say, oh, I do not like this idea of sine 1 degree in 1, it does not look good, okay, just move ahead a bit and I have sine of 1 degree, I will just increase one more step, is 0 degree plus 1 degree. So, I am using what I know is sine 0 degree plus sine dash 0 degree into 1 plus half sine double dash 0 into 1 square plus error. Now, let us see. So, I am not bothered about error at this moment, as you keep on increasing more and more terms, you know in Taylor's theorem the error becomes smaller and smaller, that is the key idea. So, I am making better and better approximations. So, sine of 0 is 0, so it is 0 plus cos 0 is 1 plus half of derivative of cos is minus of sine, okay. Cosine derivative of cos theta is minus sin theta. So, it is minus of sine 0, which is 0 into 1 plus error. Oh my goodness, it is 1 again. Guy, that is not a very good idea. Let me take the third round of approximation, okay. Sine 1 degree, so sine 1 is 1. The second order approximation is also 1, wow. So, this is not a very bad estimate that sine 1 is 1. So, sine 1 degree, if I again write in the form of Taylor's theorem, which you know, is sine of 0 degree, I am just playing along, do not worry, sine dash of 0 degree into 1 plus half of 1 by 2 factorial actually, if you go by the Taylor's theorem. So, sine double dash 0 into 1 whole square plus 1/3 1 by 3 factorial sine of triple dash 0 into 1 cube plus error. So, it is now sine 0 plus cos 0 into 1 minus plus 1 by 2 factorial into minus sine of 0 plus 1 by 3 factorial, which is 1 by 6 into cosine. Now, it is minus of sine theta. Now, you take a derivative again, it will become cos theta. So, minus of cos of 0 into 1. So, it is becoming 0 plus 1 plus 0, cos 0 is minus 1 plus 1 cos 0 is 1. So, 1/3 into minus 1 into 1. So, it is becoming 1 minus 1/3. So, it is 2/3. So, see now sine 1 degree is 2/3, it is not. So, I have a better approximation now plus error. Sorry, I am making a mistake, not 2/3, 1/6. This is 1/6, I am making a mistake. Please, sorry. I am very bad at calculations, I really admit that. And so, it is, so approximately, so from an approximation point of view, when I forget the error, so my rough estimate is sine 1 degree is 1 minus 1/6. It is 6 minus 1, 5/6. So, not very less than 1. So, it is a rough idea, sine 1 degree is 5/6, not 6/6, but 5/6, a little less than 1. But this approximation vanishes when we go very near 0. This approximation becomes much better, it will keep on giving you x. So, I am improving my approximation. Of course, the value has to be very quite near 0, because that is what it is. Now, you see I have just used addition, subtraction, multiplication and division to get my result. Knowing one value, I found other value, and that is the key idea about the Taylor's theorem. So, what happens when I want to write down something in terms of derivative, I am writing it down, then I am trying to explain things there in the board. So, let us have a function f from say R to R. And A is a given point. F has derivatives up to order k plus 1. Then the Taylor's expansion to compute fx is given as so A is known to me, it is f of A plus f dash of A into x minus A plus f double dash of A by factorial 2 into x minus A whole square plus the kth derivative of A divided by factorial k into x minus A k plus the error term. The error term always includes the error term. There are many ways of writing the error, but one of the standard ways is writing it in the integral form. The error term always includes the k plus 1th derivative. Of course, you can write 1 by k plus 1 factorial and all those sort of stuff, but you can write it in terms of, so RK actually means error in approximating fx up to k terms, fx using k terms, using k terms only. So, if I use k terms, there is an approximation of fx, f of x at x, f value at x, and there is an associated error. So, how is that error given? Rk, this is called usually the most popular one is it is by this result was given by Cauchy, the integral form of the remainder, integral form of the error or the remainder, integral form of the, I will always call it error, the people call it the remainder, I always like to call it the error because that reflects the error that you have in between this approximation and f x, because f x minus this approximation is R k, and that is given by a to x integral x minus t to the power k, where t is varying between a to x. So, you k factorial k t dt. So, this is called the integral form of the error, and this integral form has a very important property. So, what is that property? R k by x minus a to the power k, this goes to 0 as x goes to a. This is an important property of the Taylor's theorem. Okay, a pretty important property. How do we get to this form? So, let us look at what is this R k. So, you will get the idea of what is happening. X minus a k is equal to 1 by x minus a k integral a to x x minus t to the power k by factorial k f of the kth derivative at t, the k plus 1 at derivative at t dt. So, what do you do? Basically, you look at R k, mod R k, x is bigger than a here of course, mod R k, and look at this is equal to integral of a to mod of a to x x minus t k by k factorial f of k plus 1 t dt, this mod whole thing, and this is less than equal to, as you know, modulus of the integral is less than equal to integral of the mod of the function. Mod of integral of integral f x is less than equal to integral mod f x. So, integral a to x mod of x minus t to the power k, because t is lying between a and x, by k factorial f of k plus 1 by t dt. Now, what happens, most of the cases we consider this expansion, suppose we consider this expansion on this interval x a, or in the interval say in the interval a to b. So, if the k plus 1 is derivative, we assume it is continuous. So, it is bounded in this interval by standard Weierstrass theorem. So, basically you will get from here is integral a to x sum m on this x minus a to the power k by factorial k into dt. This is strictly less than m, this is less than equal to m because this is a bounded function. Okay, this is less than m. Now you divide this by, so what you do is take R k mod x minus a k, and this is less than m by mod x minus a k k dt. If you put this equal to z, dz would be dt, mod x minus a as z or whatever, mod x minus a as z. Now because x is bigger than a, this is nothing but, this integral is nothing but m by, x is bigger than a, so I can just replace this. Sorry, dt. Sorry. So now this is free of the whole thing, free of, so this is nothing but m into x minus a to the power k divided by x minus a to the power k by k factorial integral a to x dt, so it will become x minus a. So this cancels, as x tends to a, this tends to 0. So what happens? So limit as x tends to a mod of r k by x minus a to the power k, this goes to 0. And I know that I can, because this is a continuous function, assuming that if I can r k this integral, because of this being continuous as a function of x is continuous. So then I can actually take this inside. So, so it is enough to even prove mod of r k. If I put this to be 0, that is fine, right, then this because I can limit and the modulus can be swapped, because the mod is a continuous function and this is going to, so mod of something is 0. See, limit and the mod can be swapped, because r k, so mod is a continuous function, so I am using mod as a continuous function. R k itself can be thought of as a function of t. So here we are not bothered, here we are not bothered with the function of t, we are bothered with the function of x. Actually r as a function of t can be under some very simple conditions to be continuous, but that is besides the point. So here I am now looking at it as a function of x. So mod itself is a continuous function, so the limit and the function can be interchanged. That is the meaning of continuity, that whenever x k goes to x and f is continuous, then limit of f x k goes to f x, that is you can interchange the function and the limit. So which means if modulus of some quantity is 0, the quantity itself is 0. And that is what it is. So this is the key idea, that the error term, so this r k in the parlance of mathematics, r k is written as O of, small o of x minus a to the power k. That is, if I divide this by x minus a to the power k, and as x goes to a, I will get the resulting limit to be 0, which simply says that the error as x goes to a, the error vanishes faster, the r k, the error vanishes faster than x minus a. Now, that is r k goes to 0 faster than x minus a goes to 0. So, Rk is an error which will keep on vanishing very fast when x is going towards a. So, that is the key idea. So, the same idea comes in for function of two variables. I will not here give a proof of the function of two variables. What does it mean? We will do only Taylor's theorem up to second order, because we have not used higher order derivatives other than second order, because using higher order derivatives will put us into much more technical domain which we are not going to get into. Viewing the audience that I am talking to, I cannot get into all kinds of stuff, but I will do only function of two variables and up to second order. We will not give a proof here, we will give some examples of what to do. Instead of giving a proof, I will write a very interesting proof found in a book by T.W. Corner. I think this book I wanted to mention, sometimes I will bring in the class and show it. I have a personal copy, and I think this book is something you should all, those who, it is not very costly now, I hope it is not costly, and Cambridge University Press, if they have some sense, I am sure they can get it done for the Indian audience, it will be really helpful. It is called Calculus for the Ambitious. I like the title also. What is the spelling? It is correct, ambitious. So, Cambridge University Press, CUP. So, this book has a lovely way of looking at calculus, lovely, and it is so exciting even for us, for me, it is so exciting, and this book has a beautiful proof of Taylor's theorem in two variables. I will work out the proof in much more detail, and I will ask my TA to put it up on the portal. So, let us look at function of two variables. So, let me first make a first order expansion and then make a second order expansion. So, here I have x naught y naught, a point given to me, and f a differentiable function. Right. Now, this role of A that we wrote there is now played by x naught y naught, and I want to figure out the value at any f at x naught x y, and that is equal to f of x naught y naught plus del f del x evaluated at x naught y naught multiplied this thing multiplied with x minus x naught plus del f del y, this is actually an outcome of chain rule, del f del y x naught y naught y minus y naught plus the error R1. I am not writing the error in detail, but R1, the error, has to be a O of norm of, here basically we need the length, norm of the vector xy minus x naught y naught. So, this is your x, this is the x, xy is the x, so in the one variable, and x naught y naught is playing the role of A. So, this simply means O of norm of x minus x naught, y minus y naught. So, this means limit O of norm x small o, it is always called small o, these vectors x minus x naught and y minus y naught divided by the length, this x minus x naught, length of this, the norm of this vector, when x goes to x naught and y goes to y naught, this is 0. And of course, you know what is the length, this is a Euclidean using the Pythagoras theorem. You know very well what is x minus x naught, what is the norm of this? It is nothing but x minus x naught square plus y minus y naught square and a square root of this. So, that is the first order expansion first. So, we are going to be more concerned about the second order expansion of the same thing. So, we will assume that the second order derivatives, the mixed partial derivatives, everything exists and is continuous. Here we have assumed that del f del x, del f del y are continuous. So, one thing we now have to add is a differential function with continuous partial derivatives, first partial derivatives actually. Second order expansion of the same thing. Here I will write little smaller because we have to accommodate many more things here. So, second order derivatives would come. Second order expansion means second order derivatives must come. You might ask me about third order derivatives, but that will complicate things much further. So, we will not get into the third order issues. So, del f x evaluated at x naught y naught x minus x naught plus del f del y evaluated at x naught, this is the first part done, x naught y naught plus 1 by 2 factorial del 2 f del x 2 evaluated at the same point x naught y naught. Now, I am assuming that all of these partial derivatives, first partial, second partial, mixed partial, all are continuous. So, the mixed partial del f del x y and del 2f del x del y and del 2f del y del x are equal by Euler's result that we had learned, which is also called Schwartz theorem or Young's theorem when if you look at higher dimensions. So, let us have a more detailed look. So, this into x minus, sorry, here I have missed y minus y naught, x minus x naught whole square plus del 2f del x del y evaluated at x naught y naught multiplied with x minus x naught y minus y naught plus half factorial del 2f del y 2 x naught y naught y minus y naught whole square plus R2, the second order error term, where R2 has the same behavior. R2 divided by the norm of x minus, sorry, divided by the norm of x minus x naught y minus y naught whole square. What we can show is that here the thing slightly changes. This whole square, this limit as x goes to x naught and y goes to y naught, that is x y goes to x naught y naught, this goes to 0. Here R2 vanishes faster than even the square. I know that a square would come towards 0 faster than x, because between 1 and 0 x square is less than x. So, it will come faster towards 0, but here that is exactly once you make a quadratic approximation, your error vanishes faster. So, that is exactly what they are trying to say, that when x is coming x and y are coming more near and near close more near to x0 y0, the error value is going down faster and faster, that is the meaning. So, R2 is called the small o of norm x minus x naught y minus y naught whole square. So, let us now take an example and let us try to write down the first order and second order expansion. Let me take one from the exercise. There is just a simple problem rather than taking it from the. So, let me have f of x y is x plus y whole square. By the way, this Taylor's expansion of second order first thing was not really due to Taylor. These things develop much later by Cauchy and other people. So, it is not really Taylor's job. The name is given a Taylor's expansion because it is actually Taylor's expansion can be used to get this, as I will show you in the proof which will come on the portal. So, at x0 equal to 0 and y0 equal to 0, find the value of this. Let us first find a first order expansion. So, to find the first order expansion, I have to first find f of x naught y naught. F of x naught y naught is 0 in this case, and then I have to evaluate del of del x at x naught y naught at 0 0. Del of del x is 2 of x plus y at 0 0. This is 2 of x plus y at x naught 0 y naught 0. So, it is 2 of x plus y evaluated at x naught y naught, that is 0. Similarly, del f del y is 0. So, my first order expansion of f of x y, in this is a very typical case, is 0 plus 0 plus R1. So, the value at any x y, the first order, if you take a first order approximation, is the error itself. That is interesting. Now, let us come to the second order expansion. For that, we have to do del 2f del x2, and what is that? Del 2f del x2 in this case is 2, because y there is no y. Del 2f del y del x, then take y of that is 0. So, now I will take del y of this, 2x plus 2y is 2. And del 2f del y 2 is also 2. So, now let us go to the second order expansion. So, f of x y, so first order part f 0 0 is 0, this part is 0 plus 1 factorial by 2, 2 into x square plus 0 into x into y plus 1 by 2 factorial 2 into y square plus R2. So, f x y is x square plus y square plus R2. So, this is the second order approximation, right. Here it is x minus x 0, here x 0 is 0, y 0 is 0. So, it is like that. Second derivative is 2 because just check through. So, for it is 2x plus 2y. So, you take a derivative with respect to x, you will get 2 here and this 2y will become, there will be 0 with respect to x. So, it will be 2. Del f del 2 f del y 2 would be 2, while del 2 f del y del x would be 0. So, you see this is the way we keep on working, and this is the way you should express. This is enough for you to now get an idea of what the, just you have an idea how we go up to second order Taylor's approximation, but proof will come in the portal and just have a look at that. That is an elegant one. Thank you very much. It's very interesting to speak to you. I am sure a lot of young people would be listening to this. I have not done much. I do not want to put you into too much of issues at this moment. Our next thing is a much more exciting thing, my own area of research. It is optimization, it is maximization and minimization of function of two variables, and there are certain issues which as an optimizer I would like to tell you, but I would not tell you, but rather go by the book. This is the kind of issue which many people have no idea, who are not into the subject of optimization, what are the real issues involved in a problem of minimizing and maximizing. But we will go by the book, but I will try to show you something interesting, just do some interesting problems with you, right. So, that will be our, so in tomorrow's lecture there are a lot of things would be done, and so that is what it is. Thank you.